Hi everyone, I'm Liang. Came from TikTok UK System Technology Engineering team. Today I'm very glad to share some interesting finding with DPDK memory allocation. Okay, so I changed the title a little bit. I changed the title to revisit memory allocation in DPDK. The reason for that is I remember this topic was discussed in previously DPDK summit around 2019. The reason we need to revisit this is, I believe, because our fantastic tool, unit test tool, that DPDK Malloc performance test, that tool is not available back to a time. So I believe the measurement might not be that precisely. And also, today we will come with a different perspective for this, and also we have some new funding with this as well. Obviously, we will also propose a different solution as well. So we say today's agenda. First, I will do a short summary about our user case and our challenge. And the next, we will discuss a little bit about existing solution. And after that, we will discuss about the proposed solution and our POC, and also our POC's performance result, and how the benchmark environment and the setup, right? And then that's a summary. So for the challenge of our memory allocation, during my research, I just realized the memory allocation actually is an extremely complicated topic, and that's very, very sensitive with the application user case and the memory access pattern. Sometimes that's not really an apple-to-apple comparison, so it's really hard to draw some generic conclusion about that. So today, all my discussion here is based on our user case, basically, our team user case, basically. So in the following 4 challenge, first one is very easy to understand. That's the latency, right? So in the traditionally, latency is extremely sensitive with data plan, right? Data plan, because we have more and more bandwidth, 100 gig, 200 gig, 400 gig even. But recently, because our control plan's scale also increased rapidly, we found, even in the control plan, the latency does matter, okay? And the second part actually is overhead. Overhead, for the more academic term, I should use internal fragment and external fragment, all those things. But that's maybe overcomplicated, for today's talk. So I just put them all together. Just overhead basically means in order to allocate all this amount of memory, what's the price? What's the actual memory you need to use to do that? That's definitely sensitive, right, for the cost, because in any kind of service, the memory just means money. If you can save memory, you're basically saving money, right? The next one will be the scalability. Scalability is all the time is very, very important. In my opinion, there's 3 perspectives for that. First thing is, when you increase the processor number, the performance will degrade linearly, right? And also, when you increase the overall system memory capacity, the behavior will expect consistent. And the third one, also, you need to be flexible with different request signs, right? For example, for small signs, the behavior should not be that different compared with a big request sign. That's my understanding for this. The last one is really about our user case specific need requirement to how to deal with really large number of small objects. So how I define large here and how I define small here. Okay, long for short, large here basically means more than 1 million. The small object basically means something smaller than 256 bytes, generally speaking. Okay. So traditionally, DPDK memory allocation patterns, right? there's two different categories. One is for control plane, another one is for data plane. For control plane, we have the RT Malloc and RT Malloc, etc. API to deal with that. Most of them is used during the initialization, right? When you create RT ring, when you create all those hash table and when you create memory pool, etc. You will use all those kind of that setup API, not just this two I mentioned here. Also include that memory zone reserve, etc. The speed and the performance is relatively low, slow compared with the fast path, right? So in the data path, traditionally we use the RT memory pool, right? This one mainly usage for this is for PMD. So PMD will do that mbuff allocation and free, etc. And that's fix the size total, and that's really fast. I will describe that details a little bit later. But the recent years, interesting enough, more and more data plane application, like the user space protocol stack, starting use RT Malloc. So occasionally, from the mailing list, I saw some community members complain with that RT Malloc performance about that user space protocol stack usage. Okay. So this is today's RT Malloc overall architecture. Okay, that's my personal understanding. The first layer here, that's the system memory segment. Okay, you have a bunch of them. All this is organized with a list. And built on that, you have the heap list. That's another list. Each heap actually will cover one socket. So my understanding is each socket you will have one heap here. So this heap basically have two parts. One part is to link all the allocated elements all together. Another part actually is 13 buckets. This 13 buckets is depend on the size, right? As a free list. That means as a free element available for allocated from. So this is a very, very typical and classical body system setup here. Okay. For example, in the bucket 0, this one just covers 0 to 256 bytes, right? You have the free element here, and then you move on. You have the 256 bytes to 1K as a bucket 1, and etc. until to the end, the 12th buckets that cover 1 gig to 4 gig. So overall, that's a very classical body system, and each of this kind of free element can be split to smaller one, move to another bucket list, and also when you free that, these two smaller element can be merged and relocated to a bigger size bucket as well. It's very, very typical classical body system here. Something really interesting here is when the pre-allocated memory is run out, what's going to happen? What's going to happen is once the pre-allocated memory run out, then the system actually will go back to this memory segment to searching help. Give me more memory segment here. This part of logic is related to some the memory segment list sorting processing here. And then the allocator will get a new memory segment, put in this heap, and then all this list will have more free element to use for allocation. Okay, that's very important. I will use this logic in the next part. Okay, before we jump into any RT limitation here, I must highlight one thing. RT Malloc itself working perfectly, okay? Working perfectly and serves his purpose perfectly, no problem. This limitation just for our user case, because in our user case, this limitation actually have impact to our application. So I just put this kind of challenge contents here, okay? The first thing is, I just introduced a little bit about our benchmark setup. So this benchmark actually is based on our brand new unit test. That's the Malloc performance test. So we just keep request 10,000 1 meg block memory from the DPDK memory management system. And we also set up the overall memory capacity to that application with the socket limit option. That's the EAL options. You can control the upper limit of your memory assigned to this unit test. So we try with setting 4 gig, 8 gig, 10 gig, 16 gig separately, okay? That means not all your 10,000 allocation requests will be successful. Once the test will stop when the system run out of memory, have no memory to use, then stop. And then we got this latency numbers. Okay, you can easily find the latency actually not really consistent even for request the same size memory, 1 mega memory. So the latency actually increase logarithmically like this way, right? Very interesting one. I believe this is because, personally I believe this is because that memory segment list processing issues. When you run, because we do that 10,000 times memory allocation, it's easily run out your pre-allocated memory. So this end up with, you need to go back to here to searching help, right? To reprocessing with the whole list. You have more memory, basically means this list actually is longer. So your processing time may be longer as well. So I believe that's why majority reason for we see this latency increase here. And the second part for this is a heap scope lock. So if you dig into the Malloc code, it's very easy to figure out where the spin lock cover quite big scope. Basically, that scope is cover each heap. Each heap basically means each socket, right? So that's quite big scope, So this lock is not that bad, seriously for the control plane because you won't have 100 control plane cores running right in the same time, unlikely, right? Maybe 1 or 2. But this one potentially can damage your user space protocol stack performance, potentially, because the user space protocol stack actually is data plan, so can run on many cores, potentially, can impact that. The second challenge actually is from the overhead for the small object. So this is another test. This test actually, we just dump all the the overall element size the DPDK memory management system use under the actual size we request. So this is a result. So for one example, when we request 77 bytes, right, with the request size, you can notice the overall element size is extraordinarily large, right? And the reason for that is, again, because DPDK use a very, very classical, linked list to management all the allocated element. So this require you put a 2 cache line metadata just besides your pointer address. So that means each time when you try to freeze that pointer, it's very easily just do arithmetic, pointer arithmetic to figure out where is the metadata. It's very easy, very nice. But it came with a price. The price is for small object. You see, the overhead just looks a little bit large. In our case, if we're going to create 1 million, this kind of small object, our memory overhead became unacceptable in our case, okay? By the way, I need to highlight this test setup again. So this test actually is a setup based on Intel Xeon 8275 processor running with 3.0 gigahertz. And also, it's very, very typical DPDK setup. We isolate all the cores with a standard way. And also, we set up the huge page size is 1 gig. Okay, so this is a setup. And we only run this test with 1 core, 1 logical core. Okay, the hyper-threading is enabled, so I need to highlight this in advance. Okay. And we talk a lot about RTE Malloc, and then we can look into the RTE memory pool. RTE memory pool actually is a really nice design. It's fantastic for data plan. It came with some special assumption is the overall the pool size is total size that's fixed, and also for each unit inside of this pool, the size also fixed as well. This one also included the local pool. Local pool basically means here. So each logical core has its own local cache. So that means each time when it's request or free, you are not necessary to go to request the global resource at all. You needn't touch the global resource and try to avoid that even cache operation contention at all, right? And just use the local cache. And here, just a very, very standard RTE RAM-based memory pool. I need to highlight this is RTE memory pool just as a framework, API framework interface standard. Underneath, there's 8 or 7 different implementation here. This is RTE based. We also have another maybe 4 and 5 software solution. Also have couple hardware vendor solution for the memory pool as well. This one is fantastic, but this one have a very important assumption, like this fixed total size and fixed unit size. This is not really true in our use case. So this is not our solution at all. So here I would like to introduce our POC and our proposed solutions objective. So first one is I already mentioned, highlight this, right? So the RTE Malloc serves his purpose very well. The code quality, everything just good. We have no intention to touch that part of the code at all. That code running for years and robust. We don't want to touch that code at all. So we propose our solution as a DPDK library. Because we are going to deliver the presentation in Bordeaux, so I just named that API as BD Malloc and BD free. I think maybe that's interesting one, okay? And after that, all the allocation compare with the traditional memory allocators. We are just working on the Linux system heap. This one need allocate all the stuff on the huge page, okay. Also, maybe you support like a pre-allocation with kind of design rationale. And the design principle, we will do the pre-allocation. We will have the local cache. We support flexible size here as well. And we hope, ideally, we should have lower latency and a smaller overhead. But these two, just keep in mind, the lower latency and the smaller overhead heavily depend on your user case, how you use it. So I hope this is working for our user case by our design. Maybe can turn to more generic if a community put more input here. The last one is really friendly to large number small object, right? If these two actually we can successfully achieve these two objectives, I think we can achieve the final one as well. Instead of jumping into tons of details, so our POC and the proposed solution is not that complicated, but still have quite lots of details there. So instead of jump to the tons of details, I rather than use this 1,000 feet view for this POC, for this solution. Our first rationale behind this is we try to do partition. Partition means you have the control structures here, and the cache and all this memory segment here is per core. Okay, so each logical core you have all those. You don't need to compute it with any other logical cores, okay? But also, we will separate the control metadata and the place actually store the data. We will separate that one. That's a little bit different to compare with what the RT Malloc did, okay? And also, we will try to use bitmap. It's very common in kernel, Linux kernel, or other modern memory allocator to use a bitmap to tracking the element status instead of use that linked list. It's really is to save memory for small object. So the whole idea is, so first thing is we request a fixed size memory segment from the DPDK heap here. So basically, we will use RT Malloc. We request fixed size. The fixed size we use here that's configurable. Can be 4 meg, can be 8 meg, depends. So each time you will, that's how we did the pre-allocation, right? So you will request 4 fixed size memory segment from DPDK. And also, the funny thing here is because this one consistently just request one same size from DPDK. So you always came to DPDK ask same size. Not really, for this time is 4 meg, next time 8 meg, next time will be 4 KB. That's not the case. So each time you came to DPDK, say, give me this size. Okay, so this one can make the DPDK side, the body system a little bit easier. And once you grab that memory segment, with the memory segment we get from the DPDK heap, and then we will split that to a substructure. That substructure can we can name that like page. Okay, that's a very general idea. Name that like page. The page size can be 4K to 16K. It's also configurable. The 16K will more favor the bigger bigger object, and the 4K page will more favor the small object. Will give you less internal fragment. Based on this pre-allocated memory segment, we will start build up our different science lab. Okay, then we can go to another way to introduce our category in this control structure. Inside of this control structures, we will differential the different size memory requests with two kinds. One kind is normal size, another one is huge. For the huge size, what do we define here? Normally, it's configurable, but normally we define as anything beyond 32 KB. We thought that is huge. The huge one will go to use RT Malloc directly to, instead of, not really make that many sense to use our, POC. Anything under 32K here can be split to lots of different categories. That's a very traditional way you can do that with, powers of 2 or something in the middle as well. You have different, the bin buckets to hold that. So for each size, you can have this kind of slab. The slab can be 4K slab, 32 slab, 16K slab, etc. You have lots of this. So each of this kind of slab is aligned with the pitch size as well. For each 4K slab, that will split to lots of same size unit. So basically means you have lots of 4K inside. If that's a 256 slab, then you have lots of 256 bytes unit inside. So each time, when you try to allocate anything, you're just searching the most suitable slab, and for example, if you try to malloc 253, very likely give you something from the 256 slab unit. And also, we put all the metadata actually inside. For example, for the memory segment, we put the metadata in the header in the top here. We're tracking all the page status and the bitmap. And also, we will put the bitmap into the slab headers to tracking all the unit inside in the status as well. The last one, also extremely important things, is about the cache here. The cache also have exactly the same, the size bin buckets as the slab, but the different things is each time all this cache will be pre-allocated, and then when the request came in, actually the request will first jump into the cache to search if this science stuff exists or not. Okay, sorry, I should introduce what's inside the cache. The cache actually just the array of the pointer, just the array of the pointer pointing to the corresponding slab. So you pre-allocate all those slab units to the cache, and then next time when the application jump into here to request something for that science, you can just searching if the cache have it. If the cache already have it, you just give it to the application immediately, right? With really low latency. And also for the free, it's same. When the application starts free that object, you can check if that cache is not full. If that cache wasn't full, you can just put that pointer into this cache, and then the free is done. Okay, it's really fast. And then we start do some benchmark for this. So all these benchmark have the exactly same setup, compared with my first, benchmark. So for which benchmark, the setup is we do the 10,000 Malloc. Sorry, we do the Malloc 10,000 times, right? And because we never free in the middle, so that's the worst case for the whole system. Because keep request resource, we never free anything. That's the worst case for the system. And then with a very standard unit test behavior as a memory set to also 10,000 times. I believe this operation is to make sure you actually allocated something, right? Otherwise, if any allocation actually is wrong, this kind of memory set can cause corruption, okay? And then you do another 10,000 times free, and by this case, I must say the local cache not really take effect because it's so easily just run out cache. The cache just we just set most of them just 128 interest, so it cannot really support 10,000 requests, right? So it easily just run out and then turns into that slab system, and then also the slab system cannot support that because you have too many requests. Then you need allocate more slab. If the underneath memory segment is run out, you actually need to turn back to the DPDK heap to request more memory segment. That's basically a chain. So the result is very, very interesting. So this is actually a latency comparison. You can notice when the request size is very small, our POC have some advantage, have much smaller latency. Personally, I believe that's the slab system pre-allocation is working there because you don't need to go back to the DPDK that frequently. You don't need to go back to DPDK heap very frequently because most of the time you can just working with your pre-allocated memory segment. But when the request size became large and larger, you will see their performance trending to the same. I believe the reason for that is we start, came to DPDK heap more and more frequently than before. So you end up with just, have the similar performance with DPDK RT Malloc. So personally, I say this is worst case because in real life, unless you have, 10,000 times request but never free anything, right? Too greedy. So after that, I also tested with some another extreme condition is the best case. The best case basically means you just do Malloc and then free and then just repeat 10,000 times. Okay. So in this case, your local cache actually working because you Malloc free, 1 interleaved, right? Malloc and free interleaved. That's very sweet for the cache, right? So you can see the result. The result, our latency is significantly smaller than RTE Malloc, and also that's not really increased when the request size increase that much. Also, the RTE Malloc you say, I also test with blue one, you see the blue one. The RTE malloc with malloc and then free interleave the pattern, this result also is better than the BD malloc worst case result. So that means let's cross the slide. So this value actually is better than here this value as well. So the summary here, the takeaway here from this talk and interesting work, I just got a following summary. The first part is the local cache is really a critical feature for memory allocator. So we just have less lock, we have less new resource allocated, right? So pre-allocation is crucial for small object, even not use the local cache. Because we don't need to come back to the DPDK heap that frequently. So the memory overhead and the latency can be amortized with smart design, like we use bitmap actually, try to reduce the overhead here. So for next step, because this testing still is too ideal condition, you have the worst or the either worst or best, that's not real, right? So we need more testing on the real world workload. So in the real workload, that should be your malloc x times, and then your free y times. Your x, y can be very different depending on your application, memory access patterns, right? So we need to collect more real data from real world workload. And also we need to enhance our overall solution because this is a very early stage POC. We still have lots of work to do to refine that design as well. So final one is after everything settled down, we plan to upstream this to the community because I believe other community members will have similar situation with us, and we actually need something in the middle of the RTE malloc and the memory pool. This can be very helpful for everyone. The final one is thanks. So many thanks to Yubai and Dr. He Peng and Zhihong and Fan Zheng and Yu Wei because they gave me a lot of suggestions during my research work. And also many thanks to Anatoly and Dimitri for their fantastic work for the malloc preferred test. It's really, really helpful. It's just is there. This one actually is brand new, just upstream this year, I think this year March. It's very, very important for me to do this work. Okay, thanks a lot. Yeah. I think that's all for me. Okay. Any questions? Thanks.
Do we have any questions for Liang? Yes, we do.
Yes, thanks for this great presentation. Just a question regarding the algorithm. So memory allocation is not really something new, and there's the, I would say, famous TC Malloc algorithm that is used by TC Malloc from Google. And why did you decide to implement your own algorithm instead of just porting that to C?
Okay. That's a very good question. That actually is a question many people, my colleagues ask me. The TC malloc, PKT malloc, and the GE malloc, all those malloc actually is there for years. The reason we need that, I think, I need to put back to here, yeah. So the reason we need that, first thing is all those things not a part of DPDK, right? So that's just a third party library. The second part for that is all those allocator is not based on huge page. All those allocator actually use the DPDK, sorry, you use the Linux system heap as well. And also those allocator has their, they are tending to more generic. Their scheduling, their unit design is for thread, not really for core. Because in DPDK, that CPU usage, we occupy the one core, with one thread, 100%. That's our use, our CPU usage pattern. But if all those generic, memory allocator, not really designed for that. They designed for very generic thread, right? And also, all those things have lots of fancy and advanced features we not really needed. For example, some allocators support that tiny, like 2 bytes or 4 bytes, stuff. It's not really happening for us so far, anyway. We don't need any 2 bytes or 4 bytes, object so far. So that's why we make decision. We're working something DPDK natively, and can support all those things and satisfy our user case. I think that's the most important part as well. Yeah. Hopefully, I answer your question.
Any other questions for Liang?
Hi. Managing memory, no matter how you turn it around, is expensive. You'll need to consolidate the chunk, you'll need to deal with fragmentation. So even if you have some things you do know, like a set of sizes you're running on, or maybe a cache for certain something, the management is still expensive, and there is always overhead.
Okay, I got you. Yeah. So I think what you want to say is external fragment, right? So I
actually mean that. Why do you think that the correct solution is accelerate something which always takes calculation? So why not relying on pre-allocations and reusing those pre-allocations?
Okay, the pre-allocation, like a memory pool, the memory pool pre-allocation just cannot support flexible total size and unit size. For example, you create a memory pool with say 400 meg. That's it, right? You need to run this until to the end. So we need a more flexible design, and definitely you need to pay price. I get your point. Say all this kind of metadata and the control structure, that's the price. Yeah, but you gain the flexibilities. And also, you see, for certain applications like a user space protocol stack, they really need the flexible sign as well, and not just us. Yeah, thank you.
Any additional questions or thoughts, insights for Liang? Okay, well, thank you so much for
okay, thank
coming.
you.
Thank you
very much.
and giving a talk. Really enjoyed it. Great.